This is section 3.4 in Precalculus, and we're getting into solving exponential and logarithmic equations. Again, you can see the learning objectives there and the examples that we're going to talk about. Okay, so as we go forward here, first thing I want to point out to you is that if you have this is called an exponential equation when you see b to the m equals b to the n. So b is again the exponential base. If the exponential bases are the same, then obviously the exponents have to be the same, which means that m has to be n. So that's always the first step, is to make sure that the exponential equations have the same base b. Then you just set the exponents equal and solve for the unknown variable. So as a first example, here we have 5 to the power x minus 1 divided by 3 equals the cube root of 5, and we want to solve for x. So you can see from the left side of the equation that the base is 5. We have 5 raised to the power x minus 1 divided by 3. So we have to rewrite the cube root of 5 as 5 to a power, which is simply 5 to the 1/3 power. That tells us that we have the exponents must be equal because the bases are both 5. So x minus 1 divided by 3 has to equal 1/3, and you can do some simple algebra and solve to see that x equals 2. All right. Sometimes, however, when you're solving an exponential equation, you have to use logarithms because you just simply cannot get the bases to be the same. So we have to use the inverse property of logarithms to be able to bring down the power, basically, get the power down. We want to take advantage of the power rule. So we have log base b of m to the power p. We know that the power rule says I can bring this power and drop it down in front. So this equals p times log base b of m. So how do we take advantage of that rule? Let's look at the next example. We have 4 to the x equals 15. So from the left side of the equation, we can see that we have a base of 4, so 4 to the x. We simply can't write 15 as 4 to any power. If that were 16, we'd be able to do it easily, but we can't write 15 as 4 to a power. So what we do is we take the logarithm of both sides. Now, since you're probably going to be using your calculator, usually the natural log is one you go with, or log base 10, which on your calculator is just simply written as log, and also in all the literature as well. So I just tend to use natural log a lot because I like the natural log, but it doesn't matter which one of those you use. This could have been log. So what you do is take the natural log of both sides. We have ln of 4 to the power x equals ln of 15. You do the same thing to both sides of the equation, the answer is still the same. So that's why it's okay to introduce logarithms this way, which allows us then to drop this x down in front, which means the left side becomes x times the natural log of 4 equals the natural log of 15. Very simple now, just divide both sides by natural log of 4. So x equals natural log of 15 divided by natural log of 4. That's the exact answer. Put it into your calculator, take it to 2 decimals, and it comes out to be 1.95. As a further example, we want to solve 3 to the power 2x plus 3 to the power x minus 30 equals 0. We want to solve this for x to 2 decimal places. The first thing, I introduced this example because there's a few in your homework that are like this. The first thing you have to do is recognize this as actually a quadratic form. In other words, you can think of this as a quadratic equation first. Something squared plus something minus a constant equals 0. So this is called a quadratic form. In other words, you have to think of this as 3 to the x squared plus 3 to the x minus 30 equals 0. Similarly, if what I mean by quadratic form is if I had said this as x squared plus x minus 30, that would make sense to you as a quadratic form. That actually is a quadratic. In this case, this is a quadratic form where I have something with an x in it squared plus that same something minus a constant equals 0. Again, that's what we call quadratic form. So in this case, you treat it like a quadratic, which means you can try to FOIL in your head and see if you can factor it. So the 3 to the x squared has to be 3 to the x times 3 to the x. And then the factors of 30, where the difference between the two is one of these somethings, in this case 3 to the x, would be 6 and 5. So it's 3 to the x plus 6 times 3 to the x minus 5 equals 0. And just like when you're solving a quadratic, if you have a number, 3 to the x plus 6, times another number, 3 to the x minus 5, equals 0, then either the 3 to the x plus 6 has to be 0, or the 3 to the x minus 5 has to be 0. Okay, so let me just bring this down a little bit. So solving each one of these, 3 to the x plus 6 equals 0 means that 3 to the x equals minus 6. When you subtract 6 from both sides, you stop right there, because an exponential function is never negative, if you remember the graph of an exponential function. So once you get that an exponential function is equal to a negative number, you just stop. That's not possible. So on this side, we want to solve 3 to the x minus 5 equals 0. Add 5 to both sides, 3 to the x equals 5. And now I have to realize that I can't write 5 as 3 to a power. So what I do is I introduce logarithms again. In this case, I'm going to use natural log. So natural log of 3 to the x equals natural log of 5. The reason we do that, again, is it allows us to bring this x, put it down in front. So I have x times the natural log of 3 equals natural log of 5. Divide both sides by natural log of 3. And there's my answer. Natural log of 5 divided by natural log of 3. Again, if you like that to a decimal, you put it in your calculator. To 2 decimals, it would be 1.46. Okay, so that's exponential equations. Now logarithmic equations. So what do I need to do to solve logarithmic equations? Essentially, there's 4 steps. You need to write it in the form the natural log of b to the m equals something on the right-hand side. And then when you do that, after you write it that way, you want to make sure that you understand that this is equivalent to saying that b raised to the power c is equal to m, right? That's how you're supposed to read these logarithmic functions like this. This is equivalent to b to the power c equals m. Then solve for the variable, because now you have an exponential equation. So what do? You take a logarithmic equation and you turn it into an exponential equation. One thing that is a little bit different here is you need to go further and make sure you check your solutions, because sometimes when you do this equivalency, you actually can find solutions that aren't solutions for this original logarithmic equation. So you need to be careful and check all of your solutions that they satisfy the original logarithmic equation. Okay, so as an example, we want to solve the natural log of x minus 3 minus the natural log of x plus 3 equals the natural log of 2 divided by x, and we want to solve this for x. So the first thing I want to do is combine these two logarithms on the left side. Excuse me. So note when I have the natural log of something minus the natural log of something else, that's the same thing as the natural log of that first something divided by, so x minus 3 divided by x plus 3 in this case, equals the natural log of 2 to the x. Now actually I would say don't go any further as far as trying to get this as natural log of something equals a constant, because what you now have is the natural log of something equals the natural log of something, and you don't need to try to bring this natural log over here and write 0 here, because the arguments of the natural log function must be equal for this to be a true statement. So that means that x minus 3 over x plus 3 has to equal 2 divided by x. And now I need to solve that for x. So when I'm going to cross multiply. So bring the x plus 3 over here, bring this x over here. So I have x times x minus 3 equals 2 times x plus 3. It's actually in this bit of arithmetic that you can introduce some solutions that aren't really solutions to the original equation. It's when you start doing this algebra like this that happens. And so if I distribute the x on this side, I get x squared minus 3x equals, distribute the 2 on this side, 2x plus 6, and I actually can rewrite this as a quadratic equation, which this one can easily be factored to tell me that x equals minus 1 or 6. And then I have to check both of these in my original equation, and I quickly note that x can't be minus 1, because then I'm taking the natural log of a negative number in these two situations here. That does not exist, so you can't do that. And then I just check x equals 6. Certainly I'm not taking the natural log of any negative numbers up here, so x equals 6 is fine. Okay, so as another example, last example in this section, we want to look at solving for x. Log base 4 of x minus 2 plus log base 4 of x plus 1 equals 1. So now I'm taking the log plus another log with the same base, which means I can combine these two logarithms into 1 by multiplication because of the addition sign here. So log base 4 of x minus 2 times x plus 1 equals 1. Now I look at the equivalency here, right? I want to write this as an exponential equation. 4 to the power 1 equals what's inside here. So in other words, x minus 2 times x plus 1 equals 4 to the power 1, in this case just 4. And lo and behold, I end up with another quadratic equation after some basic algebra to see that x equals minus 2 or x equals 3. And again, when I go back, I check, make sure whether these are both solutions. If I look up here and I see that if I plug in x equals minus 2, I'm taking log base 4 of a negative number. Here I'm also taking log base 4 of a negative number. That's not allowed. You can never take the log of a negative number. So x equals minus 2 is not a solution. So the only solution is x equals 3.